Well, hi everyone, this is Bob the Science Guy. You know, some of the biggest questions that we have to answer in physics is the rate of change of one value compared to another value. So let me show you what I'm talking about. So let's say that we have an equation. And it gives us a curve that looks something like that. We'll call that f of x. Now we know that if we take a point here and we take a point here, we can draw a straight line between them. Now, this line will approximate the tangent line about halfway between those 2 points. Okay? As we move this line, these points closer together, we get closer and closer to the tangent at that point right there. So let's go see what that looks like mathematically. So let's say that we have a function of x equals x squared. If this is point x and we want to figure out the tangent at this point, we want to move to another point just past it. So if instead of using x, we use x plus a little bit, we'll call it dx because delta's got a big D with it. Well, that's obviously going to do something with y too. We're going to have to add a little bit to y called dy. Now let's go ahead and solve for this. So y plus dy equals x squared plus 2x dx plus dx squared. It's looking pretty good, right? Now let's remember that we're not looking at the total value of the curve, we're just looking at the difference in the curve as we go from x to x plus dx. We want to see how much y has changed. So let's get rid of the original factors of the equation and we end up with something that looks like this. dy equals 2x dx plus dx squared. Now as dx gets very tiny, in other words, if we change x just enough to not be x anymore, we're just dealing with a very, very tiny amount here. And when you square that little tiny amount, you get an infinitesimal amount. So let's go ahead and just disregard that right there. And then let's divide both of these by dx. So what do we get? dy over dx equals 2x. And that is equal to the slope at point x. Right here. So what do we know from this? Well, the slope at any point x for this equation, for this function x squared, is going to equal 2x. Notice that what we did was we took, if this is x to the n, we changed it to nx to the n minus 1. This is called the power rule. Now the only other thing that you need to know about this is if you have a constant, say 2. Recall, if you have a graph here and x equals 2, what's the slope of this line right here? It's 0. So any constant becomes 0. Now where have we seen this before? Let's take the distance equation. Now this is an equation that we're all familiar with. Distance traveled equals initial velocity times time plus 1/2 acceleration times squared. Let's apply this rule to it. So if we want to look at the change in distance over time, what's that called? That's called velocity. So if we take this equation and we apply the power rule to it, we get the change in position over the change in time. So VO stays the same. T1 becomes T0, which equals 1 times 1. So then we get 1/2 times 2 AT to the 1. So what's that equal? Velocity is the change in position over time. And that will equal VO plus AT. That's where that comes from. Let's do it one more time. Now the change in velocity over time is called acceleration. And what does that equal? This no longer has a t with it, so that it's a constant now, so that equals 0. Okay, plus a times t to the 0 times 1. So a equals a. And that's where acceleration comes from. Now, another common problem that we have in physics is trying to find the area underneath a function between 2 points. Okay? Remember that the first one that we looked for was the slope, and that's called differentiation. If we look at the area underneath the curve, that's called integration. And that is just the reverse of the differentiation. So with our power rule, for differentiation, ends up with a form like this. If we integrate from a to b, the same equation, what we end up with is x over n plus 1 to the n plus 1. So let's go ahead and just do the reverse of what we just did. Let's start off with acceleration. If we integrate acceleration in respect to time, what we're going to end up with is a t plus a constant. Because remember, if we differentiate a constant, it equals 0. So when we go back the other way, we have to figure out the constant. Now, what is the integral of acceleration? The integral of acceleration is velocity. So what is this constant? That constant is the initial velocity. If we integrate the velocity, what do we get then? Well, we get at squared over 2 plus VOT plus a c. What's the c here? That's the initial position. These equations look a little more familiar. We basically just went backwards. So if we sit there and start off with a position equation, if we differentiate that, we get the velocity equation. If we differentiate that, we get acceleration, because that drops off and that drops off. Now, what if we go back the other way? If we start off with acceleration, we go ahead and we get acceleration times t plus a constant, which as you see right here is VO. And as we integrate that again, we end up with our position equation. So that's where those kinematic equations come from. So I hope that cleared it up a little bit and gave you a little introduction into the calculus aspect of physics. It's a lot of fun when you actually start looking at instantaneous speeds and instantaneous rates of change. It's kind of a very interesting way of looking at the world. So until next time, this is Bob the Science Guy. Take care.